welcome back to another video. Today I'm going to be talking about the likelihood function, which I think is one of the most important things in statistics and probability. More in probability, but well, let's get to that later. So, what is a likelihood function? So before that, let's go into the density function. Okay. So before going into the density function, let's go into the distribution function. So the basically hierarchy is distribution function, then density function, and then likelihood function. Okay, so what is a distribution function? A distribution function f of x under x. This is the random variable and this is a number. Right, so nothing random about this, but this is random. It's basically the probability that the random variable is less than or equal to that number. Okay, that is the distribution function. So, well, let's just say we have x belongs to exponential lambda. So the distribution function of this is defined as 1 minus e to the power minus lambda x. Now, a few properties of the distribution function are, well, let's take f of x of infinity, that is basically probability x is less than or equal to infinity. Now, when I say infinity, well, that's basically a value k such that k tends to infinity. The same thing here, k tends to infinity. Now, probability that a random variable, now we are only considering real valued random variables right now. So, probability that a real valued random variable is less than or equal to infinity is going to be 1. So, fx as x tends to fx of x as x tends to infinity is equal to 1. Similarly, f of fx as x tends to minus infinity is the probability that x is less than or equal to x as x tends to minus infinity. Well, that would be basically equal to 0 because there are no real numbers which are less than every other real number. So, well, these are the two major properties. These are two of the three major properties. The third major property is that, well, fx of A is greater than or equal to fx of B, where A is greater than or equal to B. That basically shows that the distribution function is an increasing function, because let us say that fx of A is less than fx of B, where A is greater than or equal to B. That would basically mean that the probability that x, given A is greater than or equal to B, so I think this is the thing, you can correct me later on, will be less than 0. Yeah, so, and given that we know the properties of probability is always between 0 and 1, this does not hold. So that is basically that. Okay, so that's basically for distribution functions. Now, density function, the definition of a density function differs with the type of random variable. So if we say that a random variable is discrete, which means that, which basically means between each 2 points there is a gap, that is a discrete random variable. Right? Let's say we have all integers are in the, I forgot the word for it right now, but basically, let's say our sample space consists only of integers. That is a discrete one. Or let us say our sample space consists of 0, or let's just say, 0, 1, 1, 1.5, 1, 2 by 3, 1, 3 by 4, and so on. Just any random discrete function. Okay, or just a comma b comma till infinity, or basically any countable set. Well, that's the definition of discrete. Any countable set. Countably infinite set. What could be countable also? For countable finite. So for this, the definition of a density function is f of x. X is basically probability of x is equal to x. Right. So let us just look into the geometric distribution function. I think the geometric distribution function is such that the density function is basically p times 1 minus p to the power x, where, oh yes, I remember the word, support of x. Support of x is basically where the distribution where the density function is greater than 0. That is the support of x. So over here, the support of x is basically 0, 1 till infinity, or basically just z plus, all positive integers including 0. So that, this is the density function. So the probability that, this is basically the probability that x is equal to x. Okay, and for discrete, the idea is that f of x is basically summation of f of x where, f of x k, where k is less than or equal to x and k belongs to support of x. This makes sense because the probability that x is less than or equal to x is the sum of all the probabilities of all the values which are less than or equal to x. And if we tend x to infinity, k less than or equal to infinity, that basically gives k belongs to R. So that basically gets this to 1. Sum of the probability of all the possible numbers in the support of x, where the density function is greater than or equal to 0. And in the parts where k does not belong to support of x, it will basically just be equal to 0. So you can ignore that. And now if you look at the continuous random variable, well, f of x is basically just defined as the derivative of the density function at that point, right? Or you could just say I think the better notation would basically just be f of x, x minus f of x minus h by h, limit as h tends to 0. This is also the definition for a discrete case where if you remove this part, right? And now I would encourage you to think why that is true. Now the interesting property of this is that the integral over the real domain of f of x dx is equal to 1. That is pretty simple. You could just substitute f prime x and you basically get f x infinity minus f x minus infinity, which is basically 1 minus 0. So that is that. So that is the density function. Now there are some other interesting aspects of this in general. So let us say we have two random variables, x and y. We can define a joint density function, f of x and y, under x and y. This is small x, small y. Right. Now, if these x and y are independent, we can say that this is basically the density function of x under x into density function of y under y equal to. So that is a neat property. but that would require this to be independent, right? So that is mostly that. Okay, so now that we have covered the basics of all of the distribution function and the density function, I think we could go into the likelihood function. So before that, I would like to give an example of why you would need a likelihood function if you already have these two very nice functions which have pretty neat properties. So let us define a random variable x I such that let's say we have a coin. It does not need to be biased. So the coin gives heads with the probability p, and every time it gives heads we count 1. So basically it gives 1 with the probability p. So that's basically a Bernoulli p distribution, right? Each xi is from Bernoulli p. Perfect. And we have flipped the coin 10 times, n equal to 10 times we have flipped it, and we have gotten that it is head 7 out of 10 times, or basically 7 out of 10 xi's have been 1 and 3 of them have been 0. So summation xi is equal to 7. Now, using this information, what can we predict about p? Do we have any information about p itself? Okay, so one thing we can do is we can just set a value of p. Okay, and let us just say that we are given that the p's value is between 0, 0.1, 0.2, so on till 1. Okay, this is the information we are given. Now, one thing okay, my bad, I dropped my can. Yeah, okay, so one thing we can try is, okay, let us just say that the value of p is 0. How likely is it for this event to occur? Okay, so we can just say probability of summation xi equal to 7 given p is equal to 0. And we could go for probability summation xi equal to 7 given p is equal to 0.1, and so on, right? Okay, and let us say we get these values. Let's call this p0, p 0.1, and so on. What does that give us? That basically just says, okay, given some value of p, we want to say that, let's just assume that the most likely value happened. So let us say that for p equal to p0, the value is highest. So what our idea is that we are basically trying to invert the density function. Instead of finding out at what value of x the probability is highest, we're trying to find out at what value of p the probability is highest. So I will show you a Python visualization of this, but just stay with me right now. So our idea is we are trying to find a likelihood function of p given x, and we're basically defining that as the joint distribution function or the distribution function of f of x given p, right? Now we have this thing called an MLE, maximum likelihood estimator, where if you want to estimate something, we basically maximize the likelihood function with respect to p, because they're already given x, and that would basically give you the maximum likelihood estimate. So well, we could calculate all these values and we could say, okay, so given 1p, it is most likely that summation of x is equal to 7, so it is most likely that that is the value of p. It might sound intuitive for some, unintuitive for some, but I would really like for you people to think about it. So let's look at a Python visualization and see what happens. Alright, so I have written the Python file for this. So I've just imported some random libraries and choose case formula. Now these are just some variables now. Okay, so if we have each xi is from Bernoulli p, we have the thing that summation of xi is from binomial of n with probability p. or n comma p. Okay, that is just the result. So now using that, we can define the likelihood function of np, and yeah, n comma, we are basically given n and sum of x, and we are finding it with p. So likelihood is basically a function of p. Okay, and now that is basically the distribution function of, or the density function of, the binomial distribution with n comma p. Okay, so this is what it is. Okay, n choose k, or n choose summation of x into p to the power sum of x into 1 minus p to the power n minus sum of x. Okay, that is the likelihood function. Now I have gotten p. Okay, so I can just show the values of p. That is basically from 0 to 1 with 0.1 gap between each. M is base. Okay, so in each m I have filled out the likelihood value, or the value of the density function at p, or density function at summation of x with respect to p, which is basically likelihood function of pi. And then this is the dictionary. This just shows all the values of the likelihood function with respect to p. And to make it easier to visualize, I have plotted it out, and we can see the peak comes over here, which is at 0.7, which would seem likely, which would seem logical, not likely but logical, because if you have tossed a coin 10 times and out of which 7 came heads, we could just think, okay, probably the probability is around 0.7 of it being heads, or the likely value of p is 0.7, and that's what the math shows. So that is pretty interesting, and we can see that it is indeed the highest value at 0.7, around it is 0.21, 0.20. So that is pretty cool. Alright, that's it for this video, and if you like this new setup, let me know in the comments. If you want me to go into the old writing pad setup, let me know that also. Please like, share, comment and subscribe to this channel, and that would definitely make it more fun for me to make the videos, but I will still make the videos anyways because I love maths and I want to make more. And now I hope we have gotten a bit of an understanding of a likelihood function, because I will be using this a lot in my other videos. This is a really important and cool stuff. So see you later.